Welcome everyone. In this video I show you another cool little gadget that I came up with. Originally I was planning to build a slightly different device along the same ideas, but I do not have the parts for that project yet. So as a proof of concept I built this gadget. The other gadget will be built as well in the near future. So as you can see, the project is partially based on 3D printed parts. And if you look closely, you might suspect what these components are. Once I manage to peel off everything from the printing plate, you will get another look at the components. So now it is probably more obvious that I tried to print something that looks like the old computers from the 80s. I designed a chassis that has some slots and ribs to mimic the retro look for the disk drives and the ventilation. And to stick with the principles, this chassis will contain the microcontroller I use in the project. So technically I'm really working on a mini computer. Then this part is probably even more obvious than the chassis. This is supposed to be a CRT monitor. I tried to recreate the retro look by also adding some ribs. Luckily, I could print these features with my printer without any issues. The monitor has a foot, and this foot also allows to connect stuff to the PC. I wish we had such a cable management solutions nowadays. Finally, the monitor has a front panel, so it will really look like a monitor. As you can see, there are also no screws or other joints. I will simply glue everything together with a few drops of super glue. And of course the chassis also has a cover, so the microcontroller will not fall out. The slot in the center will overlap with the USB-C connector of the microcontroller. I was not entirely sure what the chassis should look like, so I really just decorated the front panel randomly. 2 disk drive slots and ribs for ventilation, plus that circular feature that should look retro enough. Also, the filament I used for this printing seems to fit the aesthetics well in my opinion. As you can see, the microcontroller has a precisely designed slot. The slot is thick enough to accommodate the 1.6mm thick PCB with a minimal gap. And guess what? I decided to use my own custom ATmega32U4 board for this task. It is an overkill, I know, but I have a huge supply of these boards at home. As you can see, the board sits well in its place and the rear panel aligns perfectly with the USB-C connector. And just as a note, the board is already pre-programmed at this point, and later at the coding part I will show you how it is done. The CRT monitor also contains an electronic part, and you can guess by now that it is going to be a display. The display is fixed using the 4 mounting holes, and the cables go through the hole at the bottom of the enclosure. Then the front panel will be glued on the enclosure to hide the non-relevant ugly parts of the OLED display module. As you can see, the display sits nicely behind the front panel. My only issue is that the display could have been square-shaped instead of a rectangle to really mimic an old CRT monitor, but this will be realized in an upcoming project. The foot of the monitor fits the hole quite tightly, so the monitor stays still and can hold its own weight, but if needed, I can rotate the monitor to adjust the view angle. So coming back to my circuit, as I showed it earlier, I marked the communication peripherals of the chip with different lines. We will use the I2C, and it is marked with dots. So by looking at the board, I can see that I will use the D2 and D3 pins. But if I flip the board, I can get even more help because I can see which I/O pin is which I2C pin. D3 is the SCL and D2 is the SDA. So quite nice. The display is a regular 1.3 inch 128x64 pixel OLED display. It uses I2C communication, so it is easy to send stuff to it. There are only 4 wires needed. The OLED display comes with a pre-soldered pin. I will remove this because I want to solder the wires directly on the PCB. I don't want any loose connections once everything is glued together in the enclosure. I use 30 AWG cables for this project because there are no large currents involved. I used relatively long cables because I will need to be able to solder the wires on the microcontroller while the display is already sitting in the enclosure of the monitor and the cable is pulled through the PC chassis. To get rid of the pre-soldered pins on the OLED display module, I just use a soldering iron with a built-in suction tool. The tip is a bit bulky, but it does the task just fine. As you can see, the holes are nicely cleaned, so it will be easy to push the wires through them and solder them. To solder the wires, I use my OmniFixo tool. It is very useful for this task. However, I struggled a bit because I placed the camera in front of me and it was not easy to reach the display without bumping into the camera or its holder. Therefore, the soldering was not my proudest job, but I put some rosin on the solder joints and reheated them to make them somewhat better. To prepare to solder the wires on the microcontroller, I thinned the stripped ends of the wires. This is mainly because they tend to fall apart when I try to push them into the holes on the PCB. To assemble the whole device, I must start with the display. The display is mounted in the enclosure by 4 M2.5 screws. But since the device won't be exposed to any vibrations or impacts, I think 2 diagonally placed screws are enough as well. Then, as I mentioned, the front cover is glued on the enclosure. 4 little drops at the corners and some pressure and weighting will do the job. Once the glue is cured, I can drag the cables through the hole on the top of the chassis and solder them on the microcontroller. Now you can see why I said that I want slightly longer cables. They need to reach the ports on the microcontroller when it is still outside the chassis. Again, I use my OmniFixel, and again, due to the weird arrangement of the camera and the parts, the soldering technique was not the best, but it is good enough. As you can see, the microcontroller slides back to the chassis perfectly. However, there is an excess bunch of wires. I figured that I can just twist the whole bunch, so it is easier to push it back to the CRT enclosure. But before finishing the wires, let's put on the rear cover on the chassis. They are fixed by M2 screws. After tucking back the cables to the CRT enclosure, the device is almost ready. But you can already see that it resembles an old PC quite well. Before gluing the final part, let's test the device. I just simply power it with a USB-C cable, and as you can see, the Adafruit logo comes up, so the device is good to go. The only thing is missing is a bit more super glue, so I glue the foot of the monitor on the chassis, and remember, the foot still allows rotation, so the monitor can be adjusted. And as you can see, the product is ready, so now let's see how to program it. So up until now, I haven't really talked about the exact purpose of this device, but if you click the video, you already know that this will be a resource monitor, which can print the RAM and the CPU usage on the OLED display that we assembled into an old PC looking device. And in order to get the RAM and CPU usage values on that display, we need to gather them somehow and send them to the microcontroller. And because of that, we need to develop an application for the PC, and that's why I have the Visual Studio open. And that's why you see that small window, because that's the application. And if you don't want to bother with the programming, then you can just support me, and in exchange for that you can download the application, so you just have to start it, and then that's all. But if you are interested in how to program this, stick with me, because it's not a long code and it's relatively easy to put everything together. So as a start, of course, I had to create a new project, and that is just done by the following steps. So you go to the File menu, and then you create a new project. And all I did is that I just started the Windows Forms app.NET framework. So that's all the project is about. And that is a form application. So it will provide you a window. Graphical user interface, if you like that expression more. So I created that project, and then I got a blank window, which was this window that you can see highlighted. And all I did, I went to the toolbox, and then you can see that the toolbox has different items in it. So these are labels, all these 3. And this label has the CPU usage printed, and this label has the total RAM and the available RAM, so the RAM usage. And then here I have my website, and actually if you click on this website, I wrote the program that way, that if you click this address, then it will open your browser and bring you to the main page of my website. But then that's all. At the bottom of the display, you can see that there are 3 other modules here. One is a serial port, which you can get from here as well. So you can see that we have a serial port. And then I also have a timer. And then I also have a notify icon. And what is under the hood, we can see it if I open the source code. So I just hide this tab here. And basically this is the source code. If I just quickly go to the bottom, you can see that it's less than 150 lines, so it's not a big deal. But yeah, we have to use a few, let's say, libraries, because we will need to deal with, for example, the serial communication and stuff like that. And then we have the notify icon and the context menu as global variables, because we will call them as a global variable. And then actually these two functions are just copy paste from Google. You can search for basically the same thing, like how to get the resource monitor developed on your PC or something like that. And on Stack Exchange you can get similar solutions. But yeah, with these lines, with this function, we get the CPU usage. And then with these lines, we get the total RAM and the used RAM. And we store them in some temporary variables inside the functions, and then we return them when the functions are called. And then we have an exit app function, which just hides the notify icon and closes the application. And then I have a hide main window function, which just hides the main window, because I will show you how this works. But by default, the application will not show up in the tray, but instead it will show up in the notification icon area. And that is a bit more useful, because your tray doesn't get bloated with all the icons and whatnot. And then of course we need a show main window function, which will show the main window once we hit it. And that just brings it back to the foreground from the notification area. And then if you remember, on the UI part, the designer part right here, at the bottom we have a timer, and the code behind the timer is this function. This is basically an event handler. So whenever the timer ticks, then this function runs. And I programmed the code in a way that the tick happens every 2 seconds. We don't need too often readings. And then what happens is that we call these two functions, which I showed you just now, and store the return values of those functions. And then I format the data based on these 3 variables into a string, which will look like something like this. And then if the serial port is open, then I send this string to the serial port, to the Arduino. And this will give us a basis, because then we will see that on the Arduino we should expect the highlighted format of values. So basically 3 integer numbers separated by commas. And we can process it. And if I jump back to the window, you can see that we print something on these labels. So actually that's exactly what happens here, is that we do not only show these values on the OLED display connected to the Arduino, but just to be sure and be able to double check everything, we assign these values to the labels as well. So I print some predefined text plus the integer value converted into string, plus another string or character, which is the percentage symbol. And then the same with the RAM as well. So that's that. Then we have another event handler, which is the resize event handler. And then what this does is that when I press the minimize button, so that tiny line up here, then the window doesn't end up in the tray area at the bottom of the display, but it calls the hide main window function, which is here, and that puts the icon actually in the notification area. So that's just a neat function there. And then the form1 load is another event handler. So when the application starts, then this is the function that runs first. This is similar to the setup function in the Arduino, basically, in this context. And we just create a new serial port here. And then we define the baud rate, which has to match the baud rate that you define in the Arduino software. I will show you how it is defined. And then we define a port name as well. And you can see that I selected the COM69. And actually this is funny, not only because of the number I chose, but I can show you how to do this exactly, that your Arduino device, or more specifically the USB port that you use to connect your Arduino device to, will have this specific number. And why I do it like this is because I want to fully automate this program. So once you have this exe file that I compiled from this short code, then this can run whenever you start your PC, because you will put it in the startup area of your operating system. And how that will look like is that the app starts, your device is already connected to your PC, and then the app will automatically look for a device at COM69 port. And then if it finds it, then it will continue communicating with the Arduino, and you will immediately see the CPU usage on the OLED display. So this is why we have this predefined port name. And once I finish with this code, I will show you how to make sure that everything will work as expected. But then we need to define these other parts for the serial port, but these are just the, let's say, default values. And then I put everything in a try-catch block. This is just to avoid crashing the program when an exception happens, but ideally nothing should happen. But if we enter the try block, then we check if the serial port is open. If it's not open, then we open it. And then if we managed to open the serial port, then we start and enable the timer, which will tick every 2 seconds. And I also create this so-called context menu, which is just a, let's say, right-click menu at the notification icon area. So when you right-click the icon of the application, there will be an open button and an exit button. So if you click on the open button, then the application will come up on the main window again. And if you click the exit, then you like permanently close the application. And then that also stops the communication with the Arduino. And yeah, we just assign the menu to the icon. And if something fails, then we throw a message box on the display and then print the exception to the display. This will typically come up when we, for example, forget to connect the Arduino to the USB. And then another event handler, which is just closing down the serial port when you close the application, just to avoid any funny things. And then this label one, I was just lazy to rename that label. That's this guy right here, my web address. This just starts the default browser in your operating system and opens my website. And then you can see that that's the end of the code. There is nothing malicious in it. I would not even be able to program that. So yeah, this is the whole code. But again, if you support me, you can get the compiled exe file as is, and then your life will be easier. So I compiled this thing, and now you can see that we have this thing open. I have quite much RAM usage now because Premiere Pro and OBS is open, plus Visual Studio and other garbage. So yeah, that's that. But my CPU is not that much used. At least the total usage of my CPU is not too bad. So that's what you see. And actually the same thing is shown on my small device. So I will try to bring up the camera and show you how that works. So this is how it looks like, and you can see the window and the small resource monitor, like the physical one, side by side. So you can see that whatever value shows up here, it's immediately updated on my display. You can see that they go synchronously. So now CPU was at 4, 3%, 0%, and they show the exact same values as it should. And this is just because here in the background, whenever the timer ticks, basically this function in the background, this always runs every 2 seconds, and every 2 seconds we update the contents of the labels here, and we also update the contents on the OLED display, so right here. So it works as it should. And now, of course, I should show you how to achieve this COM69. So the principle, first of all, is that you should select a USB port on your computer, which you will dedicate only to this device. So you should not shuffle around the connections, because then every time you shuffle it around, you would need to assign COM69 to that specific USB port that you are using. And as you can see, this COM69 is like hard-coded, so you cannot select another port. And I use this number because it's high enough that it is almost impossible that you have this exact number as a physical device. So unless you manually assign something to be on this COM port, there's basically no chance that you will have it. So then we can assign it manually. But then how it is done, it is the following. So we need to first open the device manager, and inside the device manager you should look for the ports. So this is here, and then you should look for the serial device. Of course, now you will not have COM69 here, but you should look for the COM port which belongs to your Arduino device. And then you right click it, and then you open the properties. And once you open the properties, you have to go to port settings, and you need to open the advanced option. And here you can see at the bottom that there's a drop-down list, and actually there's a huge number of COM ports that you can assign. And you really just select COM69, and then you press OK here and OK here. And now I don't have to do it because I have already done it, but you should unplug the device and plug it back. And you have to make sure that then the device shows up here as COM69. And then that part is done. And then you have to press the Windows button and the R key to open the Run terminal. And then I already entered this value previously, so it's there. This is shell : startup. And if you press enter here, it will open a window, which is the folder that should contain those applications which are not like officially Windows supported applications, but you want them to start up when you start Windows. So you should put the executable file here, and that will automatically start the application when the Windows starts up. So that means that the Arduino device will be automatically connected, and you will automatically get the updates on the display, the external display. And since now we know how to do the programming for the C# application, now we can jump to the Arduino code. So as I said earlier in the video, the board was already pre-programmed because the chip that I bought came without any kind of programming. So when I start and connect the device without anything by USB, then it shows up as a DFU device. But then it doesn't have the Arduino compatible bootloader, so I cannot really upload the data to it via USB. Therefore, I need to burn the bootloader to it. And earlier, I made a small device, which is just an Arduino-based programmer. So it's an Arduino Nano, and that is used as a programmer, this ICSP programmer. So I just simply connect the SPI pins of the Arduino to the SPI pins of my microcontroller board, plus the reset pin. And as you can see, I just used some clips to do it because I was lazy and I did not want to solder and then desolder everything. And then I went to Tools, and then you can see that I selected already the Adafruit 32U4 breakout board because my board matches the same microcontroller. And then I had to select the COM port where my Arduino was located. That depends on your configuration, of course. And then programmer was selected as Arduino as ISP. And then I just had to click burn bootloader. And then I burned the bootloader on the device. So then my ATmega32U4 based microcontroller was ready to receive program via USB. And then that allows us to basically upload this code. And the code is very simple because, for example, to drive the display, I just borrowed the Adafruit GFX library. And this 1.3-inch display, based on a different driver than the typical SSD 1306 OLED display modules. So this uses the SH110X library. You can get it from the library manager. So you go to Tools, Manage Libraries. And then in this window, you just search for SH110X. And you can see that this library pops up. I have already installed it and it's up to date. So if you don't have this library, install it and then you can use my code without any issues. And then that code comes with an example. So I was just reusing that example. So for example, the I2C address is already defined and the dimensions and the reset pin is already defined. And then I create a display here. And then I need 3 variables which are randomly assigned with some value. One is the CPU usage, and then I have the total RAM and the RAM usage. And then I also have timing variables, because what I'm trying to do here is that when the device is receiving the values every 2 seconds, everything is fine. But for example, when you shut down your computer, you don't want to maintain the display on the device. You want to turn off the OLED display because it can burn in and it consumes power and so on and so on. So there's a timer that checks if the device is not receiving data for, in this case, actually it's just 30 seconds. I was playing around with this value, so I changed it from 1 minute because I did not want to wait 1 minute. So every half a minute, if the device doesn't receive any data for half a minute, then it puts a text on the display. I will show it to you. And then it will count down 15 seconds here. And it will show this message, no signal, for 15 seconds. And if nothing happens for these 15 seconds, then the device shuts down the display. So the display will not be strained, let's say. And then when new data is arriving again, so you, for example, turn on the computer, the device automatically starts, and then it will keep showing the CPU and RAM usage. So that's why we need these bunch of variables. So we initialize the serial, and again, it's very important to match the baud rate on both sides of the app. So here, receiver, and on the C# application, the sender application. And we initialize the display. And then I create the display in a way that I erase the contents of the display if there was any previously. Something stayed in the buffer or something. And then with double font size, I print awaiting serial input on the display. I can probably show this to you with the camera. So here is our monitor, and I need to remove the power from this, and then I need to reconnect it. So we got this message, and now it is waiting here because we are not sending anything from the serial port. However, I can start my application, and now you can see that we are sending data to the microcontroller, and then the display is getting updated accordingly. So this is how this awaiting serial input works in the beginning when you start the microcontroller. And then in the loop, we are checking if there is something data coming from the serial port. And then we read the whole string that 3 numbers divided by 2 commas coming from the C# application. So we put that data into a string. And then I created a function that parses this input. So it creates 3 integers from that one single string. And then the display data function, yeah, you can guess, it displays the data on the display, on the OLED display. And then we take a note of the time in the millis when the latest serial communication has occurred. So this will keep track of that half a minute when there is no signal and the display should be shut down. So the counting starts from basically this line of the code. And then I created a function which is called check signal, and that just checks if the connection is alive. That is basically this half a minute and 15 seconds timer. So then down here, as I said, we have this predefined format, so 3 integers separated by 2 commas. And then what we do here is exactly based on these commas. So we check the first comma's position and the second comma's position, and they will help us to, let's say, drive the code to search for the certain number. And for example, I know that the first number that I send is the CPU usage in percentage, and that is between the 0th index and the first comma index of the string. So I just parse that substring into this CPU str value. And then I do similarly with the used RAM str. So I start from the first comma plus 1 because I don't want to read the comma into the number, but I want to start reading after the comma. So I add the 1 here, and then I go up until the second comma. I don't read the second comma into the number, but I go just before it or just at the comma position. So anything in between these two positions in that, let's call it array, will be the used RAM. And then finally, we start reading from the second comma plus 1, so after the second comma, so basically from here, if you see the highlighting, up until the line or basically the string ends. If we don't have any more arguments here, then the substring function reads until it hits the end of the string, basically. And then very simply, we just have these 2 int functions, and all the strings are now cast or converted into integers. And just to be safe and avoid any weird data, we know that the CPU usage is in between 0 and 100%, so we restrain or constrain the CPU usage value in between these two numbers. And then we do something similar with the RAM usage, because that should be between 0 and the total amount of RAM. So then we also do a constraint on that. And then how the display is done is that we first have to turn on the OLED display. And by default, it's on when you initialize it in the setup. But when I use this sleep function, which is based on the, let's say, lack of communication in this scenario, the display is off. So when I would start to print on it again, it would have no effect because the display is simply off. So I have to turn it back on. So what I do here is that whenever the display data function is called, I also call the display on function. If the display is already on, it has no effect. But if the display was off, then it will be on. Very, very simple. And then this is just very simple, like juggling with the numbers and the pixels and the positions. The text size is 1, because previously we might have printed something with the text size 2. For example, either the no signal message, which I will show you later, or the awaiting serial input message. Those are with text size 2. So we have to set it back to 1 before printing the parameters. These parameters, these are text size 1. So yeah, white letters. So that means that when a pixel is activated, then it's the white pixel, so the pixel is turned on. Otherwise, if you have an inverted display, then the background is the turned on pixels, and then the, letters, characters, and whatever, those are actually underscore black, because those are the off pixels. But we have a normal display, so we have white here. And then this is just where to put the cursor with a bit more fancy calculations, and then print the actual text. And then we find the position for the percentage symbol. Again, same weird scenario. And then we print it after the actual number. So you can see that here we actually print twice, because first we put the actual number, so that will be in the second line. You can see that we print 10 pixels below the previous. This is the y coordinate. And after that we put the percentage symbol there. And then you can see that we have these two bars, which represent the CPU and the RAM usage. And they are created in these two lines. And it's very simple. We scale the bar to the width of the display, and then we just put it on a 0 to 100, let's say, scale with this specific line. And then, using the fill rect function, we fill the bar, so that's the moving part of the bar, and then it also has an outline or a box, and that is the draw rect. So we draw a rectangle, and that is just based on the other parameters here. And then we do the same with the RAM. So first we just print the text, and then after that we just print this RAM usage, so how much RAM we use out of how much we have. So those two numbers, and they are separated by this slash here. And then the bar, again, it's normalized between 0 and 100% with this simple formula. And then again, we calculate the bar width. You can see how it's done. And then we draw also the frame or the box of it, and then we put everything on the display. So actually you can see that this function, the display.display parentheses, that is called just at the very end of the wall section here, because we just push everything into the memory or buffer, and then we finally pass the buffer to the display. And the final function is the checked signal function, and that just checks the elapsed time. And what happens here is that if this time was not updated for more than 30 seconds, then eventually the elapsed time will become more than 30 seconds. And then the function can enter this part. And I noticed that I need to introduce a tiny delay in these parts, because otherwise the code will not work. I don't know why. If you know the solution, please tell me in the comment section. But yeah, if this is fulfilled, so the no signal displayed value is false, so we haven't printed the no signal message on the display yet, then we enter this part. And then we literally print the no display or no signal. And then we literally print the no signal message on the display. And I can show you how this works. So here is our application, and I shut it down. And now we have to wait 30 seconds. Now you can see that the message came up. I forgot to open this window. And now we have 15 seconds or now less that this will, as you can see, disappear. So now actually, I just put this aside. This part of the code was performed. So now what happened is that we showed the display, the no signal display, and then we started a timer by passing the millis value to the no signal start time variable. And that is a 15 seconds countdown. And if that countdown is done and no serial communication is done between the device and the computer, then we basically erase everything from the display and shut down the display, like electronically shut down the display. And then we just reset this flag to false, and that's all. So now what I can do is I just put this here and I restart the application. So now I'm back to Visual Studio, and I just compile and start the app. And you can see that the app is in the background. It's not yet up. It's waiting for the values. And now it's up. And you can see that now the display is alive. And it's showing the exact same values as we see in the application right here. So it works. And jumping back to the Arduino software, you can see that actually this is the end of the software. So 160 lines of code, which could be probably more compressed, but it is what it is. And with this, I think I showed you everything and told you everything that you needed to know to replicate this project. Also, if you need a bit more details, then consider visiting my website. Link is in the description or at the top right corner of this video. I took some extra pictures and then I uploaded some extra resources, so you will find more stuff there. And if you want to have the code, the application, and the 3D printable files, please consider becoming the member of my channel. I uploaded all these resources for my channel members, so if you support me, you can access these files. And if you haven't subscribed to my channel yet, please consider subscribing. So I hope this video was useful to you. I hope you learned something, and see you in the next video.